In the last episode, we looked at a theory to replace the Big Bang. In this episode, we're going to fix redshift. Is redshift broken? Well, not exactly. We use Z to represent redshift, and it's kind of confusing. In the standard model of cosmology, with a Big Bang 13.8 billion years ago, we use this equation for redshift. Light emitted now is going to have a redshift of 0, and light from the Big Bang will have a redshift of infinity. Here are some z's in between. You see you have to go over halfway back to the Big Bang before you get to z equals 1, but then z equals infinity comes up pretty quick. The scale factor is often used instead. That's a, and a equals 1 today because everything is the same size as it is compared to what it is today. At 0.5 for the scale factor, that won't be the halfway point to the Big Bang in history. And that's because gravity and dark energy play a tug of war with the expansion rate. So you can't avoid that as long as you're in the standard model of cosmology. In the alternative model of cosmology, there's an observable limit at 13.8 billion light years. So we're in distances now. We use r for the redshift and radius. So 1 minus r equals the scale factor. You see that r equals 0 at a distance of 0 and r equals 1 at the observable limit. And the halfway point and all the other points are at reasonable logical places. So remember, light has a wavelength and frequency and an energy. As redshift goes up, the wavelength goes up, but the frequency goes down and the energy goes down. When depicted like this, it looks like redshift could be an increasing phenomenon because the wavelength is going up. But when depicted like this, where energy is favored, you can see it's more of a decreasing phenomenon because the energy is going down. Well, let me ask you this. What does it even mean physically for a wavelength to go to infinity? Doesn't it make more sense to say the energy is going to 0? You can leave a comment on what you think about that. So here's our relationships. Here in a couple examples. What is z equals 0.5? Well, its scale factor would be 0.6 repeating, and r is 33%. So that would tell us that light is 33% redshifted. It's missing a third of its energy, and it's coming from a distance of 33% of the observable limit. How about z equals 3? What's that tell us? Well, 1 over 1 plus 3 is 1/4, so that's the scale factor, and r equals 75%. That tells us that light is 75% redshifted. It's missing 3/4 of its energy, and it's coming from a distance of 75% of the observable limit. So which is clearer to you? I think r is better, but leave your vote in the comments. So let's compare. In z, in the standard model, that's an approximate distance. In what's called the de Sitter universe, it gives us an exact distance, and it doesn't really relate to anything in the alternative model. R gives us an approximate time in the standard model, and an exact distance as well in the de Sitter model, and an exact distance in the alternative model. Because space is expanding, there's a distance it expanded to and a distance it expanded from. And in de Sitter universe, that relates to z and r respectively. In the alternative model, there is no expansion in the universe, so there's just one distance, and that relates right to r. In summary, redshift can be given by z, a, or r. All are valid. The choices don't change anything. In the standard model, the scale factor a is a very natural choice. In the de Sitter universe, z and r give exact distances, and in the alternative model, only r gives the exact distance. In conclusion, if we do switch from the standard model to the alternative, it would be convenient to switch from z to r as well. So, what do you want to hear about next? Please leave a comment, subscribe. Thank you so much for watching.